Hey, I'm Jonah, and today I'll be presenting our paper, Time-Based Chart Partitioning, Improving Local Coherency in Rhythm Game Chart Generation, or TCP. This work was a collaboration with Emily Halina and Matthew Guzdial at the University of Alberta, with funding by AIIME. So our research focuses on rhythm games, and for those who aren't familiar, rhythm games are a genre where players perform inputs in time with music. So some popular examples are Guitar Hero, Dance Dance Revolution, and Osu. So our work focuses on the domain of Osumania, and this level was actually generated with our approach TCP. So you can see that notes fall in vertical lanes where each lane corresponds to a keyboard input, and players press the key at the correct time in the song. And in rhythm games, we have charts, which are like the levels, and each chart defines when and where a note appears throughout the song. So on the right, you see an example of some Osumania charts where each row corresponds to a note and its timing information. So now that we've seen rhythm games and charts, let's talk about automating chart generation. Why would we want to do this? Well, manual charting is slow and arduous. It requires syncing notes by hand, and even small sections can take hours to complete. It's highly skill intensive. Charting requires hours of practice and extensive experience with charting tools, and often a strong knowledge in music and rhythm. So by automating chart generation, we can make charting accessible to everyone. You don't need hours of practice with charting tools or music knowledge. Anyone can just generate charts to their favorite song. So how do we generate charts? Well, procedural content generation. It's been around for decades. It's used in games like Minecraft and Super Mario Bros. To generate game content like levels and worlds, and we also use PCG to generate charts. So to see where our work fits in, let's look at some prior PCG charting approaches. So first we have Dance Dance Convolution in 2017, and DDC used two separate models. The first model for note placement prediction, which predicts where the notes will occur within the chart, and the second model predicts the note types. So like an auto osu or osumania, I mean, that is like which lane the note will appear in. And this two-stage pipeline was a great first step, but we see that because the models are decoupled, DDC loses a lot of rhythmic context from the music, and its resulting charts are often very repetitive and lacking expression. So we have Taiko Nation in 2021, which is a direct improvement over DDC. Taiko Nation predicts note types and note placements in a single network. So this produces charts that are much more rhythmically coherent. But Taiko Nation struggles in that if you look at its charts, its notes are often quite offbeat and out of sync with the music. And then in 2023, we have Auto Osu, which has a dual-headed neural architecture that jointly predicts note types and note placements. So Auto Osu generally produces charts that are much higher quality than these previous approaches. However, it still struggles like in Taiko Nation, where it produces charts that are a bit out of sync with the music, and its rhythmic structure feels a little generated and AI, like you can just tell something's a bit off with it. So we've identified two main problems in current AI chart generation. The first is note placement precision. So neural models like AutoOsu are generally pretty good at finding the correct placement of notes, but if you look closer, notes are often placed slightly offbeat. And while this seems like not much, rhythm games are all about precision, so these tiny misalignments actually affect player experience quite negatively. Then the second problem is local pattern coherence. So this is the idea that that notes around each other should form musically or rhythmically meaningful. Yeah, they should be musically or rhythmically meaningful. And we can take a look at something like this nice triplet pattern. This is very common in music. We see this a lot, and it feels very good to play. Now, an example of an incoherent chart would be something like this. There's kind of these unstructured blobs of notes that just feels kind of clunky and unnatural and not very intuitive to play. So our approach, time-based chart partitioning, or TCP, specifically addresses these two issues. We have a hybrid framework consisting of a neural onset detection model and a symbolic pattern matching algorithm using a data set of human-authored charts. And TCP works in 3 phases. First, the onset detection phase, then beat snapping, then pattern matching. And I'll walk through each of these in the following slides. And again, our goal is to improve note placement precision and local pattern coherency. So phase 1, we have onset detection. So this is where we get our initial prediction of where the notes will occur during the chart. So as input, we take an audio file of the song we wish to generate the chart for, some metadata like its BPM and offset, and a difficulty value for how challenging we want the chart to be. Then we convert the audio file into a time frequency tensor representation, which is then fed into the onset detection model. And then output is our initial onsets, which are denoted by these colored bars, where each bar represents a timestamp within the chart that we predict a note to occur. For our onset detection model, we use AutoOsu's onset prediction head. I'll recall that AutoOsu was a dual-headed architecture, so we omit its note type prediction as we do that later in our patterning stage. Moving on, we go to beat snapping. So now we have our raw predictions of where the notes will be, but since neural models operate over a continuous domain, we see that they're often a bit offbeat. So here, if we look at this yellow bar, you can see that it is not totally aligned with the musical grid. So we'll use beat snapping to fix these imprecisions. So the first step, we define a set of standard musical subdivisions. Then these subdivisions will form a temporal grid across the whole chart. Finally, we'll snap each predicted onset to the nearest point on this grid. And this simple post-processing step really cleans up a lot of the precision issues we see. Then we have our pattern matching, which is the final phase. So we have our note placements locked in place, and now we want to predict our note types, so like which lane the note will occur in. So we do this first by partitioning our final onsets into time sections, and we do this using random splits. So this might look something like this. Then for each time section, we're going to search the dataset of human charts for a matching section pattern. So for example, a match would look like where we want the notes in the human charts to line up with the bars in our section target. So here, there's no match. And we use a sliding window across the whole data set until we find a match. So again, no match, but now there's a match. So if a match is found, we're going to simply copy the note types from the human chart into our list of onsets and build the chart up this way. And if no match is found, we're going to split the section further, like so. So we do this process until all sections are matched and we get a final output chart. So our evaluation did a baseline comparison against AutoOsu, and we selected AutoOsu because it's a state-of-the-art neural model. It uses the same task and domain as us, Osumania and chart generation, and it offers us a direct comparison as TCP is a modular framework, so we can essentially drag and drop any onset detection model we want. So by using Osumania, we get a direct comparison of the efficacy of our beat snapping and pattern matching algorithms. So for our evaluation, we collected a large data set of human charts, and we generated a chart each for TCP and AutoOsu and evaluated them on the following 4 metrics. First is onset precision, which is measured with an F1 score. And this looks at the timing accuracy of note placements. And this is fully focused now on the first issue that we discussed, the note placement precision. Then for the second metric, we have onset and note type precision, which is a bit stricter. It now includes note types, so this starts to incorporate a little bit of the local pattern coherence. Moving on, we look at local pattern recall, which has match rates of short rhythmic patterns. And again, this is now injecting even more of the local pattern coherency into the mix. And our final metric is note type patterns, which looks at the similarity of note type sequences, but this is completely independent of any notion of timing now. So with these 4 metrics, we kind of cover the full range of the 2 problems and the blend and intersection of each of them. So moving on to the results, before we discuss the results, just note there are 3 versions of AutoOsu. So the 3 versions are during evaluation, we assigned AutoOsu a tolerance threshold, which meant that it had a tolerance window that a match would count. This is in measures if the target note was within its tolerance window. And we don't give a tolerance window to TCP because we use beat snapping instead. And bolded results are statistically significant. So for onset precision, we see that TCP significantly outperforms AutoOsu, and this is promising. It indicates that our beat snapping does well at curbing the small timing and precision errors. Moving on, we have onset and note type precision, and there's no significant difference here. However, this is still promising for TCP as we are comparing against a fully neural model with a very lenient threshold. And at this lenient threshold, we already noticed that there's some false positives being introduced. So the fact that we matched this is quite promising. And finally, for local pattern recall, this was measured across 4 time windows from 1/4 of a measure to 2 measures. And we see that TCP significantly outperforms AutoOsu in all 4. For our 4th metric now, we look at the note type patterns, which again is the similarity of note type sequences independent of any notion of timing. So we see that for pattern sizes of 2 to 4, TCP outperforms AutoOsu, and this is very ideal because this kind of range of 2 to 4 note sizes is the majority of vocabulary in Osumania. So this is exactly where we want to be. And looking at some chart comparisons side by side, first with a simple chart, we see that both TCP and AutoOsu are pretty coherent. Not much to talk about there. If you look closely, we see that there are some timing imprecisions with AutoOsu, but overall it's pretty good. Moving on to a more complicated chart though, we see that AutoOsu is very repetitive. It kind of repeats a lot of the same patterns. Whereas if you look at the human chart and TCP, while TCP doesn't get all the note types totally same, it does repeat a lot of the same motifs, like this kind of double down, 2 doubles in a row, and its structure is overall just much more similar. So moving on to our future work, we could look at adapting TCP to additional rhythm games, as so far it's only working for Osumania. There's also an idea of global patterning, as in songs there are motifs that repeat throughout the whole song. So right now we only focus on local patterning. An evaluation with human participants would be ideal. We haven't done this, but for games, this is definitely the gold standard. We could integrate TCP with a co-creative tool to aid developers in the creation process of charts. And since TCP is a modular framework, any research into onset detection, any improvement there, we could directly implement into TCP and improve the system. Yeah, so thank you so much. Any questions?
Does the beat snapping kind of kill wave chart, or was that something you guys considered at all?
Yeah, so we incorporated a very granular set of subdivisions. So this will cover like even like quite obscure random subdivisions. However, with swing, that might ruin that a little bit. This is more focused on like pretty straight 4/4. As also same with AutoOsu. So yeah, with swing, I'm not totally sure how that would work, but it definitely is like quite robust, I would say. Yeah. We haven't looked at that. We just looked at the rhythm game, but I guess there's partitioning has been applied in a lot of different PCG applications. Um, but yeah, so far we've only applied this to rhythm games.
Yeah. I know you haven't done this one. Do you have any feelings for what people like and don't like design? Like, what would they like?
Yeah, I think it could be great at like generating ideas. And then I guess you could filter out which ideas you would like to keep or not. Like sometimes there's kind of writer's block, like you get stuck and you don't know where to go. So just having like a place to start would be very helpful, I think.